Alright, I just recorded like a 15-minute long video and like half of it didn't quite work right. So I'm gonna try to get this down in 15 minutes. I'm gonna walk through the ECS framework I've been working on. Use staff Dataframes if you want to check them out. They're lazily evaluated Dataframes written in Rust. Works with an Apache Arrow backend, and you can see what the comparisons are here. It's one of my favorite technologies to use right now. It comes with a couple caveats that require you to learn it, but it's extremely performant. I want to first introduce the concept of what an ECS simulation framework even is. And my first reference here is Esper. Esper is the Python kind of reference canonical framework for implementing these ECS frameworks. And ECS stands for an entity component system. These are just the pieces of an ECS system that kind of make up how it works. All of Esper is implemented in a single file here. Here, and it lists a series of methods and data structures that help make it work. Effectively, the usage pattern looks like this. You import Esper. This uses Pygame to provide an interactive component, and you define these components with these states as their properties. These are effectively data classes, even though they have their init methods. And then there's the, they define processors. And then these inits are just values that you might want to use inside your processor that you don't need necessarily as state of an entity. But the usage pattern is really interesting. It's saying, let me zoom in here. Give me an entity. Give me all entities for, it's going to iterate through all entities that have the velocity and renderable components. Okay. Similarly, and then it describes how that gets updated each time. The renderer processor, again, says, this is how I do it. This is how we want to process. And so these processors will run at each step of the simulation. The way that you describe which entities have these processors, let me back up. In the ECS system, entities are just integers. They represent the things that you are hoping to keep track of. They are your people. They are your things that interact with each other inside your simulation environment. This Pygame example has a window with a red square and a blue square, and they define their first entity right here. They say Esper, create entity, you get a player. Esper needs to then add a component to this player of velocity. And then similarly for renderable. And then it's like, okay, I want the renderable to be a red square. Similarly, it does that for an enemy that it describes, but remember this enemy is just an integer, and Esper is keeping track of everything in the background. Finally, you define the processors, or at least you instantiate them, and then you can define some of this logic for what key up, key down, left and right do, which is provided by Pygame. And then each step, while running, processor.process, clock.tick. This is what that looks like. So we've got this red square and a blue square. And if I go key up, the red square moves. Okay. If I try to go to an edge, it stops me. And we can verify this just quickly. Okay. So that's what a traditional ECS framework looks like. What I'm building is attempting to do this same framework with these DAF data frames. The goal being, if you're allowing this highly optimized framework that computes the optimal query plan and performs all these optimizations across the data structures, and you execute this, then the step execution should be optimized, and you should be able to run a lot more entities and a lot more processors and a lot more state. That's the idea. What I'm going to dive into is kind of how I approached it and how I'm planning on changing it. But fundamentally, if we just look at kind of the interfaces here, I've got a component store where I'm holding all of the state. The component definition, if we just look at our base here, is just a Lance model. A Lance model from LanceDB is just a Pydantic based model with a couple of helpful features for converting a base model to a Apache arrow schema, which we can then ingest into Daft. Our example that we're going to walk through is this headless example, where we're not using Pygame, we're just using our framework. And we define a position and a velocity component as well as a radius. So these are just the states of any given entity that we might want. A movement processor that says, okay, for X, the position of X, we update X based on the time, the DT that occurs across each process step. And then we have some logic hidden here that I'll dive into in a second. And then we have a wall collision processor, which is implemented with the radius. So it's not just you can't move your position. It's not hard-coded. That the radius isn't hard-coded. Everything is functionally based, right? So it's all written with Daft data frame expressions. This is what Daft tends to look like when you write it out. And as you can tell, in the difference between how we define processors, there's no for loop here. In Esper, we have for entity perform these updates. In a data frame, we just describe the updates based on the columns. The columns are directly applicable to properties from the components. So our simulation then goes and describes like a window and a max radius. And we say, let's instantiate the world. We add the processors to the world. We create some entities. And those entities will have position, velocity, and radius. States. We can then run the simulation for 10 steps, setting DT at 0.01. And if one of our balls here runs into a wall, it will bounce off with proportional velocity in the opposite direction. Since we took a components-based approach, if it's at an angle, it's going to continue at that angle and physics. Okay, there's a lot to clean up here, but I'm just going to quickly dive into what the architecture looks like because I've only got like 5 minutes here. From the interface's perspective, we've got this place where we're storing the state. And we do this by storing this component, which is that essentially this Pydantic model, base model. And we say it's type, and then we correlate that with the state data frame that we're holding for it. Conceivably, for a large simulation where you have 100 processors and 1,000 state, like components, you might not necessarily want every component, and so then this provides you with a way of querying that. I'm actually going to refactor this, I think, because this kind of insults the columnar data format that Apache Arrow comes with, and it introduces a join operation. It's extremely expensive. But before we dive into that, I'm just going to quickly mention how that works. We've got this list of entities and which components they belong to, right? And then the actual entity states for each step lie in these data frames. And then we're consistently updating that and registering new components to these properties of the component store as we move through the simulation configuration and running. Registering components means we take the component and we say to arrow schema, which is provided by LanceDB. Thank you, LanceDB. And then we add a few more columns. Okay. We are doing that for every component, which is why it's wrong. We say, okay, give me an empty table from that schema, and then give me a DAF data frame from that PyArrow table. So this creates a PyArrow table, and then we say from arrow table, give me a data frame, repartition on step, costs nothing. It just says what I want to partition on. And then we move forward. We set the component data frame. The getting a component implies that we register it if we don't have it, and then we can just get it by the get convenience method for a dictionary. And then right now I've got collections set up because I'm debugging, but I don't think that that's the long-term play. Updating a component is about setting, this is a convenience method for taking a Pythonic model that is an instance that has data in it at each property and setting that into, and adding that data into the composite data frame. Adding a component is, this borrows syntax from Esper, which we use as a part of our world building or world configuration. So in our headless test, we say add processor, and then here we say add entity, which is essentially the same thing as add component. Add component is just, it's very similar. And we can see that here. So add entity, we say now we are returning an entity and then performing this add component operation for the components added to this entity. So we can pass in multiple components for a given entity. And then we make sure that we're tracking the components registered as entities here. Okay. If we want to remove an entity, we add it to the dead entities list. And then if we want to remove a component from an entity, we take the component off of what's registered in the entities property. This is all nitty-gritty stuff. The way that this all comes together is that we have these managers that interact with the store. And they connect, so we have a query manager that has this component store interface reference so that when we pass in the component store, it knows what data to grab. And then this all comes up into the world where we have composition over inheritance for our underlying modules or subclasses, and those subclasses then have facade methods that are elevated into the world. The only thing that the world is responsible for is stepping. And then the last component that I haven't talked about is the system. A system is what performs all processors across all components for all entities at each step. So we need to be able to add processors to the system. We need to be able to process a single processor, and then we need to be able to execute all processors. And that's it.